Hello, this is John Buck again, here for another discrete time linear systems example. The example I'm going to show you today has to do with using filtering in the discrete time Fourier series. And it sort of continues on from the example we already did showing how to find the discrete time Fourier series from the signal x of n. So for this, we already showed an example where we have this square wave here, and I can actually use my little laser pointer icon here, right? So this is my square wave right here, with a period of 6. So we found this period is 6, so we put that up here. From that we calculated the fundamental frequency pi over 3. And then we went through the Fourier series equations to find that for this signal the Fourier series we needed 6 coefficients. A of 0 was a half, A of 1 was a third, and by symmetry we found A of minus 1 is also a third. A of 2 was equal to A of minus 2, which was 0, and A of 3 was equal to minus a sixth. And this is all in the video, the previous video I've done. So if you're not familiar, you might want to go back and look at that and review it to see where these coefficients came from. Today we're going to go on and look at these and say, well, what happens if I put these coefficients through a filter, which I give is specified by its frequency response. And particularly for today, we're going to look at the low-pass filter. So let me sketch the low-pass filter here. So I'm going to have a filter. Looks like this, where the gain is 1. This is my omega axis. Oh, that's a terrible omega. Try that again. This is my omega axis. And my filter, my low-pass filter, I'm going to put the cutoff frequency at pi over 2. And then over here on the negative frequency axis at minus pi by 2. So that would make, if I sort of space it out proportionally, this is minus pi to, or I'm sorry, that's pi and this is minus pi. And when we draw a frequency response, we specify it over one interval that's with 2 pi, usually from minus pi to pi, because the discrete time frequency repeats outside that axis. And we write this, we say it's h of e to the j omega. So this is the frequency variable up here in the exponent. It's a little confusing it's that way, but there's actually a good reason we'll see for it later when we get to the z transform, so that all the frequencies are on this axis. And in fact, we might go mark right now. We said we know that the discrete Fourier series is equal to fundamentals, right? The frequencies we work with in the DTFS. The frequencies we're interested in are at, well, we can call them omega sub k because it's different for each k, and those are equal to omega naught times k. So in this case, that would be pi over 3 times k. So when k equals 0, I'm just going to mark these maybe in different colors with red to show where we're interested. When k equals 0, this will be at 0, which is right here. So the gain at that point is 1, actually. So I guess this should be more like an arrow to show where they are. Then this would be, I'm going to move that back a little bit out of the way so I don't get the, so let me continue this. So I'll put this down here. When k equals 1, well, on the frequency axis, that will be right here. All right, this was the k equals 0 term. And then over here, pulling this back, this is where I would look for the k equals minus 1, right, which is minus pi by 3. When k equals 2, I have 2 pi by 3, which is a little more than pi over 2, so that would be right here. So this is my k equals 2 at frequency. And this is my k equals minus 2 frequency. And then right here, the last but not least is my k over 3 frequency, right? When k equals 3, pi over 3 times 3 is pi. and that puts it here. So what this figure sort of makes clear is, although I may have this whole omega axis, the only points I actually care about are the points that are multiples of omega naught, which are right here, right here, right here, right here. There's k equals 1, 2, and 3. And we'll see once we get some practice with the filtering relationship, that helps us figure out which a sub k's we actually need to compute. If we hadn't already found the a sub k's, we have them already from the earlier example. But if I didn't already have them, this would tell me, once I know how to use the filtering relationship, that the only ones I actually need are these three where the gain is 1. All the ones over here where the gain is 0 aren't that important. So let's go on to the next page. Let me see if I can use my clever cut and paste things to bring things with us to show you how we're going to go find. Well, I should sort of start by marking that up on the next page. So let's go to the next page. So our problem here is to find y of n. So our goal on this, wrong color. I can go up here and say our goal here is to find y of n. Okay, in order to do that, our approach to doing this, our goal is we're going to first, to do that, we're going to start with, we're going to find the Fourier series coefficients for y of n. So we're going to find the DT FS, which for y of n we'll call it b sub k, for y of n. And the way we're going to do that is we're going to use the filtering relationship. And I'm going to sort of write this in a little complicated way, but hopefully to emphasize something, which is that we know from the filtering relationship that we have b sub k here. So the Fourier series coefficients for the output are equal to the frequency response. So that's h of e to the j omega naught. And again, I'm going to put this in red to emphasize it's the same k, so that all the k's get replaced the same way. Times a sub k. Okay, so again, the Fourier series coefficients of the output for each value of k, you take the input one and then multiply it by the frequency response evaluated at this frequency, right? The frequencies we just marked are this thing here, omega naught times k. I take that back to this axis and say, well, what was the gain? What was the value of h at that point for this value of k? Okay, so to go ahead with that, let's bring some of the information over from the other page, if I can use my cut and paste. Okay, so let's try to, we're going to need the filter here to remind us where these values come from. So I guess we'll put it on a new page here. So we have the filter. And we're also going to bring back the a sub k's. So let's see, we want these here. It's not grabbing very well. There we go. So let's take this block up here and bring it with us. So to do this right, I got to put it in the library, then come over here. Oh. Oh, that moves the whole page. That's not what I wanted. Oh, a pointer. Maybe this helps. There we go. So this is I'm going to put my frequency response up here. See if I can. I've got this extra F. Can I clean that up? Apparently not. Let's go to the library. See where it went. No. That's not it. All right. I apologize for the waste of time here. I thought I could just do that, but apparently I didn't. I should have rehearsed that ahead of time. So let me just write them down again to remind us what they are. So I've got, again, for the a sub k's, I have a of 0 is 1/2. A of 1 is the same as a of -1, which is 1/3. A of 2 by symmetry is the same as a of -2, which is 0. And a of 3 is -1/6. So now I'm going to go through to find each of the b's one at a time using the same formula, right? So b, if I go back to that page and remind you, nope, that page moved ahead on me. I'm going to use b of 0 is h of e to the j, and this is 0 times a sub 0. So let me write that down. So b of 0, or consider maybe at least the first one until it gets tiring. I'll do this color change to remind you here. Why am I not erasing? There we go. Now I erased the whole thing. All right. B of 0. I'm going to overdo it on the color for a little bit so that you can see where all these terms are coming from. Is equal to h at e to the j, and then I have 0 k times omega naught, which is another 0, right? Because when k is 0, times a, again with the same k, which is 0. So all this is the k equals 0 term. Yeah. And so now I just need to go plug those values in to get the answer I need. So I say, well, I've got all right, my color thing hates me tonight. H at 0 is this point right here, right? When omega, I use the exponent here is actually the omega axis, is the frequency axis. Some people find that a little confusing at first. So the value here is 1 because that's what the line is at, the height is at. It's not because e to the j0 is 1. We'll see that has to do with the complex plane later. I just read off the height here and say this is 1. So this is 1, and then a of 0 was 1/2. Right, and I got that from up over here. So bringing this together, this tells me the Fourier series for the output of this signal will be 1/2. Okay, going on doing a similar thing now, I can go find the, let's do over here maybe the k equals 1 term. So when I do that, find the Fourier series coefficients for the output. B sub 1 is equal to h of e to the j, and then I have omega naught times k. Well, now omega naught and then k is 1 for this term. So again, I fill that in up here. Right, and then I say this is times a of 1. Oh, let's see, I've already lost my strategy here. This should also be red, and this should be red. So all the k's have become 1s in this equation. Hopefully the color makes that a little easier to pick up. So now I go here and say, well, what is h of e to the j? Omega naught, we saw already, was pi by 3. So that was this point here. So again, the h at when omega equals pi by 3, the gain in the filter, we say, is 1 still. So this will again be 1, and then times a of 1 up here was 1/3. So this tells me the second discrete Fourier series, the coefficient, the b sub 1 coefficient for the output is 1/3. So I'm sort of finding the output one piece at a time, or as I said in class, this is like a recipe, so I'm figuring out how much of each ingredient one at a time. Well, you can use the same idea, or use the symmetry idea here, and say, well, b of minus 1, right, so I set k equal to minus 1 for this term, is equal to h of e to the j omega naught, and now this k up here would be times minus 1, right? So this is, if I bring all that together, that's like saying I have the frequency response at minus omega naught. Oh, and I still need a with a k replaced by minus 1. Now you don't want to or go to the trouble of making all these things different colors on your homework. I'm just doing it now to emphasize that I'm plugging in the same k for all three of these. So that's to sort of bring your attention to how these things are linked, which component of the Fourier series determines how I do this. So now I go up here and say, well, minus omega naught is minus pi by 3, right? This was the k to the minus 1 term. So still the gain is 1. So I have a gain of 1 here. And a to the minus 1 was the same as I had before, as 1/3. So I again have a gain of 1/3 here. So this was my, again, just to make it clear where these things came from, this was my k equals minus 1 term. Going on to something that actually changes the pattern a bit, let's look at k equals 2. Well, it's the same. I shouldn't say changes the pattern too much, because it's the same idea, right? I still have b sub 2 here is equal to h of e to the j, and now my frequency axis is omega naught times k, and that k is 2. Right, so again, overemphasizing the whole color thing here. And then I use that to scale a sub 2. So this is the way that, again, the nice thing about the filtering equation is I worry about one value of k at a time. And so now I go and look at this and I say, well, let's plug in the values the same way I've been doing. So this one gets really easy really fast, because I say, well, first of all, I go look at what h is at this point. Well, here it's outside the passband. The gain here is 0. So I've got 0, but also my a sub 2 was 0. So I've got 0 for both of these. So the output, that says there's no output, or the output doesn't have anything in this, what we would call the second harmonic, or the k equals 2 harmonic. Okay, so going on in the same pattern, I'm going to sort of finish off the last two coefficients here. B sub minus 2 is equal to h of e to the j. So I'm taking again the frequency response at omega naught times k. So again, I've set k equal to -2 for this whole equation. And I'm using that to scale the input Fourier series, which is a sub k at -2. So again, this is the k equals -2 thing. And again, by not surprisingly by symmetry, this one, if I go back to the previous page, is, well, this is 0 here for the gain, and it was also 0 for the input Fourier series. So just as I had 0 times 0 for k equals +2, this will be 0 times 0 for -2. And finally, the last term, we get the output for k equals 3, right? Because the period was 6, I need 6 Fourier coefficients. And I'll get h of e to the j omega naught try to clean that up. Omega naught times 3. So 3 omega naught is the value of the exponent scaled by the j. So that's where we want to go look at the frequency axis, times a sub 3. Right, so this is my k equals 3 term. So again, I can go back to the last page and say, well, k equals 3 times omega naught is pi over 3 times 3 is pi, and again the gain there is 0. So if I go forward again here, this one again I have 0 for h, and a sub 3 wasn't 0, it was minus the 6, but it turns out not to matter. The filter has removed this component, so it's gotten rid of the third harmonic. Right, so if I come back here, right, a sub 3 was minus 1/6 I had found in the earlier example. But this filter, because the gain is 0 at that frequency, at pi, it's removed that component. So now I've got all my coefficients. I'm going to start on a new page. I've got all the pieces I need, so I can go ahead and do a new page. And to find y of n, I use my discrete Fourier series equation. So I know that's the sum as k. And again, the way I chose the k's, they go from -2 up to 3. B sub k e to the j k times omega naught times n. And I'm going to sort of remind myself over here, because I'll need it later, that omega naught is pi by 3. But I don't want to plug it in just yet, because it'll turn out to be less to carry around. And so now I could go, and I guess if I really want to be consistent with my earlier thing, is to remind myself all the k's everywhere when I'm plugging them in. It's going to be minus to 3. I'm going to plug in the same k down here that I do up here. And I go through these one at a time. So when k equals -2, well, b sub -2 I had on the last page. Right? And I had this was 0. So I can just put this in here. So when k equals -2, I get 0. Just doing this sum one term at a time. I just count my way through them. The next term is the k equals -1 term. And that for that one, I had the b sub k for that one. Turns out it was a third. Right, so I get 1/3 e to the minus j omega naught times n. Right, because I said this k equal to -1 gives me e to the minus j omega naught. The next term, I do my k equals 0 term, and I get 1/2, should be weight, e to the j 0n, right? Which is just, this term here really is just a fancy way of saying that this is 1, right? E to the anything, and the exponent to the 0 power is 1. Going on to the next term, when I get a k equals 1, I have again b sub 1 was a third, e to the j omega naught times n, bad n. Try that again. There's a better n. Okay, and again that 1/3 came from here. B sub 1 was 1/3. So I put in the 1/3 for the b sub 1, and I had e to the j omega naught n. And then the last two terms, for k equals 2 and k equals 3, are both 0 because b sub 2 was 0 and b sub 3 we found was 0, right? We found the b sub 3 was 0 here because the filter set it to 0. B sub 2 was 0, well, it was, back up, there we go. B sub 2 was 0 because both terms were 0. So now I have this term all written out. And again, once you get some practice, you don't have to write all these out with the k underneath each one. But just, I'm really doing it step by step to emphasize each thing here. In practice, we'd usually go right past that. So now let's write these out and change things around. I'm going to put this term here first, because I have an ulterior motive knowing where I want trying to end up with the answer. So I have 1/2 plus 1/3 e to the minus j omega naught times n, and plus 1/3 e to the plus j omega naught times n. And my ulterior motive here is recognizing this is something I can use Euler's formula to simplify. So I get 1/2 plus 1/3 e to the j omega naught, well, minus omega naught n, and then plus e to the j omega naught n. So this term in brackets here, term in brackets is 2 times cosine of omega naught n. So if I pull all this together to simplify, it's 1/2 plus 2/3 of cosine omega naught n. Now maybe I can plug in, now is probably a good time to plug in for that. So let's put omega naught in here from taking this value from up here. I have 1/2 plus 2/3 cosine of pi by 3 times n. And I can go through and plug in one value at a time for n to get this system. I've already sort of done that ahead of time. I know what it's going to look like. And so I'm just going to sketch this out quickly. This is at n equals 0. And that's sort of what I'd expect. It's a DC plus a cosine that repeats with the same period of 6. This will be 7/6, and then at n equals 1, it'll be just down a little bit from that, it'll be 5/6. And the same thing at -1. This is 1, sorry, this is 0, minus 1. This is my n-axis. And n equals 2 I can plug in here, and I'll get 1/2 plus 2/3 times, this will be cos of 2 to the pi over 3 is minus 1/2. So that will leave me with plus 1/6 for the height. And then at 3, this is actually going to be minus 2/3. This will be cosine of pi, which is minus 1. I get amplitude of minus 1/6. And after that, I start getting the repetition from the periodicity. So it'll be back all the way up to height of 7/6 over here when n equals 6. This is the 5th sample. And the same thing going the other way. I'll have the 1/6 minus 1/6 here at minus 3, and then bouncing back up, and so on periodically. So this would actually be at minus 6. So there's drawing 2 whole periods of the signal. So again, you sort of see a cosine envelope here with an offset, a DC offset. The middle point is 1/2, even though we never actually get a value of 1/2 out of this thing. So that's a long-winded, very thorough Fourier series filtering example. I hope you find that helpful, and good luck until next time.